This is the second in a series of videos about solubility. In the first video, we talked about intermolecular forces and how similar intermolecular forces for two different compounds will allow one to dissolve in the other. And in this video, we will talk about pressure and temperature and how that affects how much of a solute can dissolve in a solvent. So let's talk about pressure first. And pressure is only a concern for the non-condensed phases. So pressure does not affect the solubility of liquids and solids. And if you think about it, this makes sense. If you were to compress a liquid or a solid, make it smaller and smaller and push really hard on it, you wouldn't really be changing the total volume very much. These are already very condensed phases. However, if you were to compress a gas, which is very spread out and takes the full space of its container with lots of empty space between particles, you would cause a change. You would be able to compress that gas. And because of that, changes in pressure cause a proportional change in the solubility of a gas. So let's draw a picture here. Let's say we're going to make a soda. We're going to be dissolving carbon dioxide in water. Here's some carbon dioxide. Here's whatever the liquid is that we've dissolved it in, probably water. So at a particular pressure, we'll show the pressure with our force arrow from the gas law chapter. At a particular CO2 pressure, you're able to dissolve a certain amount of CO2 in a solution. So now over here, let's say we have the same amount of solution, but let's say we increase the pressure. So we'll put a second arrow. 2 arrows, such pressure. Okay, so if we increase the carbon dioxide pressure on the top, we should be able to dissolve more carbon dioxide on the inside. Proportionally more. Sorry, that was a little fuzzy there on the camera. Okay, so the main idea is gases are more soluble at high pressure. So, as you may have guessed, we can quantitatively describe this qualitative relationship. And a guy named Mr. Henry figured that out. And he said the solubility, which is C, remember, solubility of a gas is proportional to the pressure of a gas and multiplied by some constant. That constant is called KH, or Henry's constant. He named it after himself. Or rather, someone else named it after him after he died. This is our solubility. And solubility is measured in the same units as concentration. That's moles per liter. This guy, K sub H, that's a constant, Henry's constant. And that is substance dependent. So there's going to be a different constant for every different substance at every temperature and pressure. So this is a widely varying constant that you probably won't find in a table because there's so many of them. This is our partial pressure of the gas. Okay, so let's look at this formula in action. Let's do an example problem. So let's say we have a carbonated soft drink, as we are all want to drink. Carbonated soft drink at 25 degrees has a partial pressure of carbon dioxide of 4 atmospheres and a concentration of 0.124 molar. What is the carbon dioxide concentration after the bottle is exposed to air, room temperature, room pressure air, which has a partial pressure of 3.0 times 10 to the -4th, much lower than that pressure at the beginning. So there is a strategy for solving these Henry's law types of problems. And it's one that we've already used as early as the gas law chapter, and that is to separate this into two situations, an initial situation and a final situation. In the situation one, we should have enough information that we can solve for this constant because it's too difficult to look it up in a table, so we can solve for it with a set of data instead. So we can find that constant from situation one data. And then once we have that constant, we know that constant is going to be true for that same substance in a different scenario. We can use the constant with data from situation two. Okay, so that's our strategy. So now let's try solving that problem using our said strategy. So situation one, that's at the beginning, that's back when the drink was being carbonated. So we said 25 degrees Celsius, pressure 4 atmospheres, concentration 0.124. So we'll use Henry's law, C equals K times P. We'll plug in the concentration here for the solubility, solve for that constant, and plug in 4 atmospheres for pressure. So substitute. Now we'll solve. And we should find a value of 0.031 molar per atmospheres. Okay, so that's our constant. And the units can be whatever you can dream of in this case. The units match whatever the other variables were. Just know that whatever units of pressure and concentration you used at the beginning, you will need to use in the second situation. So situation two, concentration equals Henry's constant times pressure. In this case, we are assuming it's at the same temperature. We know that the bottle is open to air at this particular pressure, and we're trying to find the concentration. So C is equal to that Henry's constant. We're going to take from our situation 1.031 molar per atmosphere, and our pressure, which is the actual pressure of CO2 in the atmosphere on the surface of Earth, which is very low. So now we can solve for the solubility, and we get a much smaller number, 9.3 times 10 to the negative 6 molar. And we always do the bullshit test when we do our calculation to make sure our number makes sense. So we'll go back here. We had a very high pressure of 4 atmospheres and a high concentration of 0.1 molar. And here we have a much lower pressure, 3 times 10 to the negative 4th, and a much lower concentration, 9 times 10 to the negative 6th. So we passed the bullshit test. This is a reasonable looking number. And this is why all of the carbonation comes out of your drink when you leave it open, sitting at room temperature. Okay, so that's about how pressure affects the solubility only for gases. And now let's look at temperature. So temperature affects all solutions, not just gases. And so we want to look at a plot here. There we go. Okay, so what we are looking at here is we are looking at solubility versus temperature for methane, oxygen, carbon monoxide, nitrogen, and helium. So these are all gases at room temperature. So this is the solubility of gases in water. And if we look at our other figure, We've got solubility in water versus temperature of sugar, potassium nitrate, sodium bromide, potassium chloride, sodium chloride, and cesium sulfate. And these, you might not know some of these at the bottom, but sodium chloride and sugar, we know those are solids. So solubility of solids in water. So let's look at that. So the first thing you see when you look at this picture, besides the obvious rainbow colors that bring us joy, are that all of the lines in this gas side picture have a negative slope, and all the lines over here have a positive slope. Except this one, I guess this one is different, but most of the lines have a positive slope, negative slope. So what does that negative slope means? It means that at low temperature, we're going to have pretty high solubility. And as we increase the temperature, we're going to have low solubility. So let's draw a little fish who's in the water. And let's look at how the oxygen is dissolved in the water. So this is water, we're in the ocean or something. That's what waves are for. So if we're at a pretty low temperature, cold, the solubility of oxygen, which the fish needs to breathe, is going to be pretty high. So lots of oxygen in the water for this fish. So the fish is going to be happy because the fish has something to breathe. All right, let's look at the other situation. Deep down under the sea, after some factory dumps super hot thermal waste into the water, if we're at a warm temperature, we're moving over here to this part of the graph, the amount of oxygen we can dissolve in the water is lower. So maybe there's only a little bit of oxygen. The solubility has decreased. And now our fish is dead because the fish does not have any oxygen to breathe. This was a pretty big part of my life up until I moved to California because my husband worked with salmon. And so the salmon like to live in cold water because there's lots of oxygen easily soluble for them to breathe. If the water gets too warm, all of the fish die because they have no oxygen to breathe. Important stuff. Okay, then let's check out the solubility of solids. So we'll do our cold first. We are going to have tea in this picture. Okay, so if we have tea and it's at a pretty cold temperature, we'll put like a little one little bit of steam coming out of the top. And let's say that I want to put honey in this tea because I'm a wimp and I don't really like the way that it tastes without some sugar in it. So how much honey are we going to be able to dissolve in this tea when it's cold? As you may have known, if you've ever tried this, is when you add the honey into the cold tea, all the honey just ends up sitting at the bottom. Because it's a solid and it has a low solubility at cold temperatures. Luckily, we know what to do. We know how to get that honey dissolved in the tea so that it tastes less yucky and Rachel is willing to drink it. All we have to do is heat it up. Heat up the tea. Notice there are 4 steams. That's hot. So if we have a warm temperature, you're going to be able to just absolutely dump honey into that. We are going to be able to dissolve lots of honey in our warm tea because liquids have high solubility with high temperature. So if we were to summarize, we could say the solubility of solids in water is going to be directly proportional because as we increase the temperature, we increase the solubility. And when we're talking about gases, it's going to be proportional to 1 over temperature. because as we increase the temperature, we decrease solubility. Proportional to temperature for solids and for gases. Hope you have enjoyed these pictures of fish and of coffee mugs. The reason I went so long into the pictures is because it can be difficult to remember which trend is which for solids and gases, which increases and which decreases. But if you can think of a real life example in which you're trying to dissolve one thing in another at a particular temperature, you should be able to remember the relationships between the two. In the next video, we will talk about distillation and vapor pressure of a gas over a mixture of liquids.